Okay, so welcome back to the lecture series of finite volume, and as we recall, we are just looking at the deferred correction approach using two different methods. One is the downwind weighting factor method, which we have discussed, and we have seen the shortcomings of that method when from a multi-dimensional system to one dimensional system. When we go, we can easily or could easily see what is the problem with that approach, and there could be some remedies. And now what we are going to discuss in this particular lecture is the NWF, which is the normalized weighting factor. So, that is what we are going to talk on in this lecture. Now, we have seen that if issues with the DWF, now we will similarly formulate the NWF, and here in this case the one would try to, so this one actually try to address some of the issues of DWF method, so that we can have a better platform or framework. So, it operates by linearizing the normalized interpolation profile such that phi f tilde would be looking like L phi c tilde plus k. So, that is a sort of a linearization, and L and k, these are all constant that represents the slope. L represents the slope, k represents the intercept of the linear function within any interval of phi f with the number of interval depending on the HR scheme which is being used. So, this is an exact representation for nearly an all HR scheme that we have already discussed earlier. Now, for example, in normalized variable formulation for mean mode scheme, if you look at that, the values of L and k that we have obtained there is like this: 3/2 0 for range where phi tilde goes from half to 0, then half where phi c actually goes between half, and then 1 0 which is elsewhere. So, these are the values of L and k which we have already derived while looking at the HR scheme. Now, second step is to rewrite this ratio phi f minus phi u divided by phi d minus phi u. That ratio one can write L multiplied by this factor and then plus k. So, that is what one can do, which can be transformed to a system where one can write the face value phi f equals to L into phi c minus phi u plus k into phi d minus phi u plus phi u, which is L phi c plus k phi d plus 1 minus L minus k phi u. So, where phi c is the cell constant, phi d is the downstream node, phi u is the upstream node, along the flow direction. So, this will be the flow direction. So, that is how the representation of the nodes which are being used, and this is pretty much consistent throughout our lectures what we have been following with the notation system. Now, L and K, these are the values L and for a number of higher order scheme, and this is the values for a number of HR scheme. So, which we can see for different kind of scheme what are the values. So, let us say this is again in uniform grid with NVF formulation. Then what one can see for upwind L and K, this will have values like 1 and 0. Now, second order upwind which will have L and K is 3/2 0. Central difference scheme, these values would be half half. From, so this should be 1/4, 1/4. Now, when you look at quick, the value would be 3/4, 3/8. Now, we have already seen for mean mode the value has a different segment. One is 3/2 0, it could have half half, it could be 1 0. This is the range where phi c less than half greater than 0, phi c less than 1 greater than half, and elsewhere. So, similarly for Pochar, the LF value, LK value will have again 3 segment. One is 3/2 0, 0 1, 1 0. Here the phi c goes between 0, phi c tilde goes between 1 to 2/3, this is elsewhere. Muscle scheme, it will have a segment of 4. So, 2 0, 1/4, 0 1, 1 0. This is phi c when lies between 0 to 1/4, when 1/4 to 3/4, 3/4 to 1 elsewhere. And similarly, the smart scheme, where this will also have segment of 4, 4 0, which will get you 0, 3/4 by 3/8, 0 1, 1 0. This is 1/6 to 5/6, 5/6 to 1, this is elsewhere. So, one can see that different L by K value can be obtained on a uniform. Now, for unstructured grid, this upstream node or U is virtual. So, the term involving phi U is treated in deferred correction fashion, but the resulting source term, which would be for unstructured, the resulting source term which will be in form of 1 minus L minus K phi U is smaller than 1 would be obtained with the standard deferred corrections. So, that is what it would give in your unstructured system. So, the NWF requires less under relaxation than the standard deferred correction method. So, obviously, if you require less correction, NWF requires less under relaxation, which will lead to faster convergence. So, if you have that, now we will start from our equation which we are dealing with, this phi f. So, the phi f that we are having is L phi c minus phi u plus k phi d minus phi u, which is finally written as L phi c k phi d 1 minus L minus k phi u. So, we start with that. For a general case multidimensional grid, m dot f phi f can be written as m dot f 0 L f plus phi c plus k plus phi f, then 1 minus L f plus minus k plus phi u plus minus m dot f 0 L f minus phi f plus k f minus phi c 1 minus L f minus k f minus phi u minus. So, this plus and minus goes in the. So, if you linearized, then you get flux f f m dot f k f plus minus m dot f L f minus flux C f m dot f L f plus minus m dot f k f minus, and flux V f m dot f 0 1 minus L f plus k plus phi u plus minus m dot f 0 1 f L f minus k f minus phi u minus. Then once you substitute all these things, the discretized equation is obtained as AC phi C plus F NBC AF phi F equals to BC. So, system looks similar, but the differences would come in the coefficients, like here it would be flux FF, which is Kf plus m dot F 0 minus LF minus m dot F 0, AC, which is flux Cf NBC LF plus m dot F 0 minus m dot F 0, and your BC is QC VC minus summation of these fluxes, flux VF, which is going to be QC BC NBC 1 minus LF plus minus Kf plus phi u plus multiplied with m dot F 0 minus 1 minus LF minus Kf minus phi u minus m dot F 0. So, this is the term which is due to deferred correction, or the source term due to deferred corrections. So, that is how in your NWF formulation the discretized variable would look like, and they would appear in the discretized system. Now, this one was initially developed. There is a small thing which is associated with this one. This was initially developed for unstructured grid, and with this formulation which allows a full implicit treatment of the HR scheme. But what is happening, the full implicitness of the method on unstructured grid of phi u, which is being an actual node in the computational domain, that can be resolved in the algebraic equation. So, that has now a larger stencil that includes the far nodes EE and WW. Now, for the one dimensional system, like what we have done for the 1D system, C, E, W, E, WW. For 1D system, this again we can simplify this particular set of multidimensional formulation to 1D, 1D NWF formulation, and there it will be AC still phi C plus F goes from E west E WW AF phi F equals to BC. So, where your AE would become flux FE, which is m dot E KE plus minus m dot E LE minus plus m dot W 1 minus LW plus KW plus. Similarly, the AW is flux FW, which is MW 0 multiplied with KW plus minus MW 0 multiplied with LW minus plus M dot E 0 multiplied with 1 minus LE plus KE plus. AEE, which is going to give you the flux FE, which is minus M dot E 1 minus LE minus KE, and AWW flux FWW, which is minus M dot W 1 minus LW minus KW. So, AC is summation of NBC flux CF, which is M dot E 0 LE plus M dot W 0 LW plus minus M dot E 0 KE minus M dot W 0 KW minus. So, that is nothing but your minus AE plus AW plus AEE AWW plus M dot E plus M dot W. So, that is what you get. Now, what that does, this NWF formulation, that HR schemes L is greater than that of K. So, provided there is a narrow region of NVD close to the downwind line, and that we will see how it happens. The second thing is that the value of AC is always positive, and that is why. So, AC is always positive, and that makes the system is a stable system, or the instability does not arise. Now, along the downwind line of NVD, where your downwind line NVD in our variable diagram, my L and K, it should be 0 1 a value of 0 for AC coefficient is obtained. So, in this case the L and K can be set to capital S 1 minus L phi f, where L is usually set to the value of L from the previous interval of the scheme. So, what it brings down to, the moral of the thing is that NWF to be much more robust than the DWF scheme, because it always guarantees this coefficient AC to be positive, which does not lead to any instability. Now, the previous derivation was based on the NVA formulation. Now, we will look at this NWF method in the TBD framework. So, now we want to see, so what happens that except that Marshall Van Leeuwen limiter, all the limiters of the TBD scheme actually will be presented along a straight line in the TBD CBC or psi r diagram. So, and one can write that psi RF is a MRF plus N, because all of them except Marshall Van Leeuwen limiter, all other limiters will follow some sort of a straight line there. Now, M and N, these are constant, one is the M is the slope, N is the intercept of the linear function and depend on their geometric equations within an interval of psi RF. Now, the number of intervals, it depends on the high resolution TBD scheme. Now, for example, let us see what happens to this particular equation if you equate with the mean mode scheme. So, for mean mode scheme, the value of M and N would be 1 0, 0 1 or 0 0, because in this range RF is less than 1, greater than 0, RF is greater than equals to 1, RF is less than 0. Now, once we use this psi RF definition and then we try to evaluate the phase value like phi f equals to phi c plus half of M RF plus N phi d minus phi c. One can do little bit of algebra here, which would be half of M phi c minus phi u divided by phi d minus phi c plus N and phi d minus phi c, which will again lead to 1 plus half M minus half N phi c plus half N phi d minus half M phi u. So, again phi u, phi c, phi d, it will follow the flow direction. So, the values of M and N one can find out all that for the different schemes, and also so the one thing that you can obtain like this particular expression when you has the same form as earlier expression, like if you write in this form phi f equals to L phi c plus k phi d 1 minus L minus k phi u. So, if you compare these two, what one can write is that L plus L equals to 1 plus half M minus N by 2 and k equals to N by 2. This is what it gives you back. So, once you look at the similarity. So, we will stop here and we will continue the discussion in the next lecture. Thank you.